Okay, we're going to start, so settle down. So we're going to continue with 1.3. We're talking about linear models. We've already seen a couple examples of this. One was that hot dog example when I had to figure out how many hot dogs I can sell at a certain price. It ended up being modeled by a straight line. In that case, it was actually told that you would use a straight line because I told you that there's a linear relationship. I gave you a second example about a car rental company and how their cost structure is set up. And that gives you another hint to know when a linear model is being used, when something changes by a fixed absolute amount. So this is about linear models. You know so this is just a review. We need to use a linear model, meaning you're going to set up a function to look like a straight line, and we're going to talk a little bit more about straight lines today. You know that you need to use a linear model if, one, you're specifically told to. Right, so there are sometimes you'll see a problem on a test and it will say, these two things have a linear relationship. It will specifically tell you the relationship between these two quantities are linear. And there are multiple reasons for that, not only because it's a test, but sometimes you're not sure how things are related in real life, and so you kind of first set up the simplest model that you think might work, and then you kind of check to see if it does work over time. So sometimes it might make sense to you to think that two things are related in a linear fashion. So to capture that idea, some problems would specifically tell you that something follows a linear model. And two, if you are, maybe this is not as comprehensive a word, measuring a quantity that changes by a fixed absolute amount. On regular intervals. And the intervals might be time. You can say it changes by this much every hour, every day. Or it might be in terms of distance every mile, right? So you're changing by the same value. So that was like the rental thing where I said it charges, I don't remember, $2 per mile or something like that. So every mile you increase by the same value, $2, right? So anytime you have something changing by a fixed absolute amount, and absolute means in terms of the size of the value, right? $2, right? I'm going to distinguish that between something like a relative amount or a percentage amount later. But absolute amount means it's the same value that you keep adding to the thing or you keep subtracting from the thing. And whenever you see one of these two situations, you know you need to set up a straight line to model the scenario. Okay. So now let's remind ourselves about straight lines. Okay, so let's make sure we're all on the same page here. Give me an equation for a line.
Y equals x.
Huh?
Y equals x.
A general formula.
Y equals mx plus b.
Okay. So y equals mx plus b. This is called the slope-intercept form. Of the equation on the line. Here, m is the slope of the line. And b is the so-called y-intercept. So if we look at pictorially what's going on with the line. So you have a line doing this. This here, remember, is the y-axis. That here is the x-axis. But this guy here This point is called the y-intercept. It's where it touches the y-axis. There's also the x-intercept. I'm not going to go into full detail about this because I know you've seen lines over and over, but I just want to make sure that everyone's aware of what I expect you to remember. We could go through, why does that have to be the equation of a line? Why is the slope measured a certain way? But we can all skip that. Given, and I think this, I asked this on the quiz. Given 2 points on a line, you can find its slope, m. Say we have 2 points, which I call x1, y1, and x2, y2. Then, is the formula that gives us the slope. Yeah?
It's y2 minus y1 divided by x2 minus x1.
And make sure the order matches up, right? Technically you could do y1 minus y2 and x1 minus x2, but you need to make sure you subtract them in the right order, right? These two must correspond to one point and the last two must correspond to the other point. It doesn't in general matter which order you pick. Which point you choose to be y1 and y2, it actually doesn't matter. Just make sure you do it in the right order. So that's how we find the slope. That's a very important equation. That's the slope when you have 2 points. This you can also remember as rise over run, right? Because if your line, let's say you have that 1 point, x1, y1, and then you have x2, y2. Then if you want to find this distance, so-called the rise, that's going to give you y2 minus y1. You take the top number minus the bottom number. If you want to find the run, the distance between these two, then that's going to be x2 minus x1. That's called a run. Right? So you take the rise over the run, and that gives you the slope. Right? This is a measure of the steepness of the line. Given a point, x1, y1, and the slope, and you can also find the equation of the line using y minus y1 equals m x minus x1. Basically, you let y2 and x2 be a generic point, just let it be a general x and a general y, multiply both sides by the denominator, and you end up with this form. It's another important form of the equation of the line. It's the most convenient one when you already know a point and the slope. This is called the point slope form for the equation of the line. Personally, I find this one more convenient to work with, but you can always simplify to get the other form if you'd like. Another thing you want to be aware of is about the sign of the slope. And what that means for your line, and what that means for the function as a whole. So in the 2D plane, there are really only 4 possible cases for a line. Either the line is moving up as you go from left to right, or it's moving down as you go from left to right, or it stays steady as you go from left to right, horizontal, or it doesn't move as you go from left to right. It's a vertical line. In this case, what is the sign of your slope? It's positive. In this case, it's negative. In this case, 0. In this case, it's undefined. We all know. There's another interpretation I want us to always be aware of when we're talking about lines as well, is in terms of increasing and decreasing. This one is increasing, right? I gave you that definition last time. This one is decreasing. And this one is neither, right? You can call it non-increasing or non-decreasing or something. Okay? So in terms of the slope, less than 0. In terms of the slope, you need to know when it's positive, when it's negative, what it means in terms of increasing and decreasing. And that can also help you interpret a lot of word problems. So I could say something like, these two things share a linear relationship, but this is decreasing. So you know the equation of the line you set up needs to have a negative slope, right? Or if you have some other reasons for believing that it's decreasing or increasing, you need to be aware that the slope you need to set up to model that situation has to be negative. It's decreasing. Now I doubt I said anything that anyone didn't know, but now you kind of know. That's something that you need to be aware of with lines, how to set one up. So you can set one up given 2 points. You can set one up given 1 point and a slope. There's another phrase that I want to apply here, but I'll actually wait until we get to something first. Here's another way I want you to start looking at things. And I'm going to pick a very suggestive example so that you can actually see where I'm coming from right away, but just be aware that this actually will apply in general. And let's just say that this object is moving in such a way that its speed is remaining constant. So let's say, and it yields the following graph. So on the vertical axis, I'm actually going to measure the distance. I will measure the distance, again, to be very suggestive, in terms of miles. On the horizontal, I'm actually going to measure the time I'm tracking this thing. So I'm going to measure time here. I'm going to measure that in hours. So let's just say this object is passing a certain point and I start my stopwatch. So at that point, I say its distance or its position is 0 and the time is 0. I track it for a while, and it's moving at that. And say after 2 hours I track it, and I can measure its distance here that it has covered 80 miles in 2 hours. Find the slope of this line. What is the slope of this line? What's the slope of the line? Yeah?
40.
How did you get that?
Rise over run.
It's rise over run. Okay.
Yeah, I just did 80 divided by 2.
Okay, so the rise was 80, and the run was 2. Right, so that gives us 40. Right, and you could also have realized that this was 0, 0, and this point was 2, 80, and you could have done the y2 minus y1 in this section. So now, that's not very interesting. I just said there's an interesting interpretation of the slope. How do you interpret that number 40? Yeah?
As like miles per hour.
Miles per hour, right? The rise is measuring the y, but that's measuring distance, that's measuring miles. So this 80 is not just 80, it has an interpretation on it, it's 80 miles. This 2 also has an interpretation on it, it's 2 hours. So that 40 is actually in miles per hour. And what is that? What kind of quantity is that when you have miles per hour? This guy is a speed. Technically, if you want to be very pedantic, it's a velocity. But you can sort of think of it as speed. It's how fast your distance is changing with regards to the miles. So in other words, from now on, when you think of slope, I don't just want you to think of rise over run, or it's just this formula. It's kind of a measure of speed. It's a measure of how fast the thing on the vertical axis is changing with respect to the thing on the horizontal axis. And there was nothing particularly, I mean, we recognize the speed because these are units that we're used to, and that's how we measure speed. You know, we take the miles, we divide by the hours, that's how we figure out how fast something works. But the math doesn't actually care, right? If I put here number of items sold versus price, the same thing would apply, right? That's measuring how quickly the number of items you're selling is affected by your change in price over some time. You can think of it as a speed of price versus number of items sold, right? You can think of it as, and here's the phrase, so when you're a math person, you start to think abstractly, and you realize that, you know what, this doesn't really depend on what I labeled this, because that's how you find the slope. Right? So there's nothing special about the miles or the hours. You can think of slope, at least the slope of a line. As the rate of change. That's a buzzword in calculus. In fact, in general, I can think of the slope of a line as how fast y is changing with respect to x, whatever interpretation I want to put on y and x. With respect to, WRT is short for with respect to. Regardless of their interpretations. So rate of change or speed also, it still stands that negative slope means decreasing, and positive slope means increasing. So if I'm figuring out how fast y is moving with respect to x, I can also actually interpret from the sign of the slope what direction is it moving. Is the y getting bigger or is it getting smaller? Right? So I can tell you how fast it's getting bigger or how fast it's getting smaller. Now, last time I mentioned to you that when we were talking about the slope of a line, I told you that a lot of calculus, about half of it, is based on the simple fact of us recognizing what the slope of a line is. This is the other part of the puzzle, right? The fact that not only can you recognize that the slope of a line is important, but that you can actually put an interpretation on it that falls right out of the math itself, right? When you think of slope, from now on, as a calculus student, whenever you hear that word, you don't just think y2 minus y1 over x2 minus x1. You don't just think rise over run. From now on, when you hear the word slope, you think speed. How fast is it changing, right? And that interpretation is what's going to make calculus, right? That's where you move from algebra to calculus, by just reinterpreting how you're looking at the numbers. Right? And it all is based on a straight line, because this is one of the simplest kinds of structures, mathematical structures, that we know how to measure, a nice way to measure speed, right? Like if I gave you this random function, how fast is y changing with respect to x? I don't know. How are we going to measure that? You know, we don't have a nice rise over run kind of thing to do here. Okay? But with a straight line, it's actually pretty easy. We all know the formulas. We've known them for years at this point. Okay? But this is a very important interpretation for the slope of a line. I'm not going to do any more examples. I think you have enough to do your homework. But that's sort of the end of 1.3. But if there's one thing I want to impact you at the end of this lesson, because I feel like you've known everything else I told you at this point. But if you didn't know this is what's important to remember. Right? There will come a time where I'm going to ask you, how fast is this changing? And you need to know, I need to look at the slope in order to answer that question. Okay? And again, you know how to do it for a line, but that's not good enough. Calculus comes into play when I want to do it for something that's not a line, when I want to do it for something random like that. How do you measure the slope of something like this? Calculus is the answer. We'll stop there. I'll see you guys on See you guys tomorrow. And I finished this section, so the homework for this is 1.3.